topic that we're going to do that is helpful rather than me just sitting up here saying, does everyone know the way to get to ketones and aldehydes? Because that gets a little boring, right? Not that any of this isn't boring, I recognize. But we aren't going to go there. So, the first one we're going to do is Wolff-Kishner reduction.
Yay.
Okay? So this is what I've purported as reduction of a carbonyl that's attached to benzene. The Clemmensen reduction does work there because the benzylic carbon has different redox properties than a typical carbonyl carbon. It doesn't work as efficiently on like 2-butanone. So like that zinc mercury catalyst that you like to use, Clemmensen reduction, doesn't work efficiently on sites that are not directly attached to the benzene. So the Wolff-Kishner reduction still is your friend. If you haven't recognized that, it's coming back and it's very friendly to you. It works all the time. Okay, so let's remind you of what that is. So if we take, say, 2-propanone, right? The Wolff-Kishner reduction conditions were to take hydrazine, which is NH2NH2, okay, with a little bit of acid, and then follow it up with KOH in H2O as a 1-2-stepper, right? So what happens at the end of step 1, you now know, right? So at the end of step 1, if we were just to follow this through into the subsequent steps, if I add now hydrazine, at the end of step 1, I get to something like this. I get to an imine, right? Should be able to mechanistically show, this would be the first mechanism in Wolff-Kishner reduction, should be able to show how to get this imine from the starting material, okay? So we showed imines as important sort of intermediates along like a reductive amination pathway. This is importance of an imine along the pathway of creation of or removal of a carbonyl, right? That's also important. But I guess I'd be hard-pressed to say that once upon a time, these imines and enamines were actually important to us because they allowed us, for identification purposes, to identify what ketone or aldehyde we started with. Now we have spectroscopy, right, NMR, and NMR really has been a wow in terms of being able to put together exactly the carbon backbone. But once upon a time, you would not know what ketone or aldehyde you had in your hands as an unknown identification exercise. And I'm reticent to say I did this when I was in college. I was given an unknown ketone or aldehyde, and I had to go make an imine derivative. And then I took the melting point of said imine derivative, and I went to these large tables looking up all the potential melting points, and then coming back to what potentially my ketone or aldehyde could be. I got a subset of possible choices, and from there I worked with other reactions. Sometimes I made a different imine derivative because some of them had different melting points. So I would use that sort of concept to wheedle down to my unknown. Now it'd be easy to go throw this in an NMR tube, right? Put it in the NMR and get an NMR spectrum, and wham, bam, you're good. But so imine derivatives now I'm trying to purport as utility in a different direction, not just identification purposes. This being one of them, our reductive path here to remove our carbonyl. So at the end of step 1, we're here, and at the end of step 2, we said that you would fully remove that entity there, and in a 1-2 step, you get all the way back to the alkane. So really the mechanism that we're going to work through today is this step 2. This mechanism here, right to here, you should be able to do hands down, eyes closed, the whole 9 yards. Okay? So you might want to practice that. It's a good one to try and go practice. So in terms of step 2 here, let's start with what the mechanism is going to look like. So I have base in its conjugate acid, water, and the proton that's likely to be abstracted here is the one off the nitrogen. It's got a lower pKa than the hydrogens off of the carbons, so this is the most likely site for deprotonation. So on first deprotonation here, we've grabbed that hydrogen. Hydrogen leaves behind an electron pair, right? Makes conjugate base. that electron pair pops up onto this nitrogen. Okay? So, in this case here, you get to now something that looks like this. Okay? That's the conjugate base. I've put in the electron pairs now, just so we can keep track of the charge. It was neutral, that nitrogen was neutral to begin with. It had one electron pair on it, this guy out here, right? One electron pair and 3 bonds. Now the fact that it has 2 electron pairs, and I'm providing my card, you guys are all looking at me. 2 electron pairs and a negative charge shows how the formal charge of -1 comes to bear. So, in terms of a resonance structure I can draw, resonance structure is actually this one. So these are resonance structures of one another. And it's from this resonance structure that we can see the subsequent motion through the mechanism. And that is for this conjugate base to pick up a proton from water. Now this is another place that I warn you, you all choose, when something's negative and you go make it positive, you choose acid. I get why you do, but we have no acid in here, right? So really you have to pick up from the neutral water molecule, and it's going to create more OH minus in solution as this occurs, okay? Should never, ever, ever have positively charged species in this second reaction from henceforth, because here we're in basic conditions, okay? So we pick up from neutral water. And the outcome of this reaction, this acid-base reaction, regardless of this acid-base reaction, which I think does have some reversibility associated with it, this acid-base reaction has no reversibility associated with it. Okay, if you analyze the pKa's, and that might be a good thing to do, because the exams, questions, relegated in the mechanism section, parse out some of these steps, singular steps from mechanisms, and ask, is this reaction reversible or irreversible, this exact step? And you need to understand why this exact step would be reversible or irreversible. I'm trying to purport here that we're seeing a step here which we haven't seen in a long time. And that is an irreversible step, right? And this step is irreversible because we have a carbon base picking up a proton from water, and the acid-base chemistry, if I analyze the conjugate acid and the acid, we'll see is such that the reaction is irreversible. There'll be a great difference in pKa's from the left to the right, okay? So water at 16, the alkane at 60, big difference, okay? So we're seeing an irreversible step. So in this case then, we picked up a hydrogen here, and we're back up to the top. We have one more proton that we can pull. So while this might have some reversibility associated with it, we pull our last proton here, okay? And we analyze what we have. So we look at that. We have something like this now. Okay? Now this actually is nitrogen gas. I hope you recognize this. This looks a little bit like one of the intermediates we had along the aryl diazonium salts, right? Whereas if this electron pair came into form this here, right, you would actually form N2, N triple bond N, right, which is nitrogen gas. Yeah?
Why would the oxygen pick up the hydrogen in the first place? I mean, aren't both nitrogens in a happy place in a way?
So the bottom line is, though, that we don't, your question is a good question. It's a static question, though. And nothing is static in chemistry. That's really one of the big overarching problems we have in chemistry, is that things are always happening. Nothing just sits. You know what I mean?
Yeah.
And so these protons are moving all around, all the time, okay? What might we have more in population in terms of total population in the flask is based on the thermodynamic properties of that acid-base chemistry, but that is always happening. I mean, I recognize you're saying this is neutral, this is charged, but nothing's static, right? So we have a constant flux here. And as you come and you bear out some of the end products, especially these irreversible steps, they drag the whole reaction along, right? So just in terms of probability, sort of a Le Chatelier's principle. Okay, so everyone sees that this is nitrogen gas, right? This is nitrogen gas. And nitrogen gas falls off. It doesn't need its electron here when it falls off, so it leaves its electron pair behind. That's what happens when nitrogen gas falls off. This is a different leaving group concept than what we usually see, right? Because we usually see something like this. This Br falls off, meaning the electrons go with it, right? That's different than what I'm trying to say now. Now I'm saying that we have something like this, and as this forms nitrogen gas, it doesn't need to take these electrons with it, right? It's got to leave them behind. So be careful of your arrow here, okay? Does everyone understand the difference between my arrows? What I mean when I say falls off? Okay, great. So it falls off, and I create now another carbon nucleophile that again is going to pick up hydrogen from water. And what we get in the end is two hydrogens on what was once the carbonyl chemistry. Once upon a time, long, long ago, it was a carbonyl carbon, and now that carbon is just an alkane. Yes?
That step's irreversible also, right? When the nitrogen falls off.
When the nitrogen falls off, this is irreversible too. So I have some slight reversibility here. We're going to go look up the pKa's of these species. I actually don't know what the pKa of this guy is. I would guess it's something like 36, but I'm thinking it might be a little bit different because of what it's bringing with it. So I'm going to look that up. If I assume this is 36, right, there's definitely some reversibility associated with this, right, for sure. But this is an irreversible step. This would have some reversibility associated with it. This is irreversible, right, when nitrogen gas comes off. And this acid-base chemistry is irreversible. The bottom line is that you're never going to go, ever going to go, from an alkane to this starting material, this imine, in base and acid, right? Because this sequence becomes irreversible the minute I have a single irreversible step. Okay? I'm pausing for sort of emphasis. In a given reaction mechanism, if I come upon a single irreversible step, the entire mechanism, right, is not reversible. Okay? You might be able to get back to that one species, but you'll never get all the way back to the starting material. So this is a departure from a lot of the chemistry we've seen with ketones and aldehydes. This step here, while I didn't put it in because I was using just the reaction arrow to put in conditions, we know that this step here is fully reversible, right? The imine formation is fully reversible because every single step in that reaction mechanism is reversible, which means it's fully reversible, all right? Whereas this step here is irreversible because I have a single irreversible step, of which there are really three, but my point is you can have a single irreversible step and it would become irreversible overall. Does everyone understand that for emphasis? Okay, so I believe that this is our last mechanism, okay? This is our last mechanism that we've done. So as I try and do, as I come in and I leave a unit, I'm going to work with you to make a reaction tree for alkynes, okay? What we can use to get to an alkyne, what we can use an aldehyde, or what we can use to get to an aldehyde or ketone, and what reactions we've learned with aldehydes and ketones. So build ourselves sort of a summary, okay? Then we're going to try a couple retrosynthetic problems, and then we're going to pass out our reaction scheme that we can work on for a few minutes, and you guys can ask questions, and we can work on some of the stuff that maybe has gone by you in the past, meaning from Worgo 1. All right, so in summary then, the heart of our tree here is our aldehydes and ketones. Okay. And with my aldehydes and ketones, the first question I pose to you is, what reactions do you know are going to create aldehydes and ketones? Oxidation of alcohols. Great. So you can do some sort of oxidation. I'm just going to use this O, oxidation, to state that you could start with alcohols. You need to go back and remind yourselves everything we talked about, right? The difference between primary, secondary, and tertiary alcohols. But yes, you can take alcohols and oxidize them. Your conditions would vary. So if you started with a primary alcohol, PCC is the only way to go. If you start with secondary alcohol, pretty much any of the oxidative mechanisms are available to you. Okay? So you can oxidize an alcohol. What else can you do? Yeah. Great. So you can do ozonolysis, which is O3 followed by some reductive condition, right? You can actually start with alkenes or alkynes. Okay, great. So ozonolysis is a propensatory way. To note about ozonolysis, right? You'd start with a much longer chain. You cleave or clip the chain when you do ozonolysis, right? So if you count carbons, if you have a larger number of carbons in your starting material compared to your end product, you've probably done an ozonolysis reaction, right? Just thinking logically, trying to help you think logically about that, okay? Reminding you. Should be one other that you should be able to think of to get to aldehydes and ketones. One more.
I was going to say oxidation, but I don't think that's it.
Oh, come on. You guys make me do all the work. Okay, you can start with alkynes, and you can do some sort of hydration reaction, right? This is a stand-in for hydration. There are two types of hydration reactions we talked about. One is mercuric catalyzed hydration, H2O, H2SO4, HgSO4. And the other is dicyamylborane, followed by an oxidative workup. Those created enols, the category enols, right, which then tautomerized to give us ketones and aldehydes. So these are what we know. Okay, so in summary, we have learned that you can get back to alcohols, right? I guess we'll just do it in the front. So you can get back to alcohols. What sort of reagent do we use to get back to alcohols? Sodium borohydride? Anyone?
Lithium.
Or lithium aluminum hydride. But we're going to use sodium borohydride because
It's less.
it's less dangerous. That's exactly right. Okay. What else can we get to? Get to what? Alkanes? Sure. Okay. But maybe we can say imines and enamines, right? Imines themselves, we were able to get to alkanes, not enamines. So that was KOH and H2O. How do we get to imines and enamines? Yes, that's right. We add amines and acid. Okay, great. What else can I form? Primary amines give us imines. Secondary amines give us enamines. That's not on here, but you're absolutely right. Yep. Tertiary amines give me nothing. That's exactly right. Good. What else can I make from ketones and aldehydes?
Oxides.
I can make carboxylic acids. Okay, we didn't talk about those reactions, but you're absolutely right. From an aldehyde itself, so maybe I should be clear about that. From an aldehyde, you could use some sort of reagent to give you carboxylic acids. I'm cheating, COOH, faster than writing carboxylic acid out, but we're okay with that, right? What else can I get?
Ethers, ketones.
I can get ethers. Okay, ether linkages. You're talking about acetals, hemiacetals, ketals, hemiketals. Sure. So I can use sort of ROH and H plus and get to hemis and then acetals and ketals. That's totally right. All right, what else can I do? alkenes. I can get to alkenes. That's totally right. What do I use for this? The Wittig reaction. I've got to say it like a true German. Come on. A Wittig reaction. Okay, great. What else can I do? Can I make an alcohol from a Grignard? I can. Now that alcohol is a little bit different than the NaBH4. So for that, I'm going to keep it sort of a little bit separate. You can make alcohols here. Okay, but the difference here is that you actually extend the chain, right? Whereas here you don't. Does everyone understand what I mean? You can have a chain extension, or you can add carbons to your backbone by using a Grignard and reacting it with a ketone or an aldehyde. There's other carbon nucleophiles you can use as well, right? We had a cyanonucleophile. We have an acetylide, which is the triple bond, say ethine. If you want to think of the IUPAC name, ethine. We do use a deprotonated ethine. Anything else anyone can think of? Yeah.
Ethers through epoxides?
What?
Ethers through epoxides?
I can get ethers through epoxides.
Or no? Way off?
No.
Okay.
Okay. The other one that is good to know is that I can get amines here. So this is the last one I'll put on here. I'm not saying this is totally finished, but certainly we talked about reductive amination, right? The formation of imines and enamines that then I can do some reductive amination with. Okay? So this is a good summary. It's a little busy, I realize, but it's a good summary of what we know. Okay? So as we get our synthetic hats on, okay, we're going to put on our little hats. My dog goes to the vet, gets on the party hat, which in essence is the muzzle. And we're going to put on our synthetic hats, though. And we are going to try and see how, what starting materials, I guess we could say, I would need to get to these final products. Now let me tell you, because this is the disclosure on the, I don't know if that's the right word, but on the next exam, we're testing you on ketones, aldehydes, and carboxylic acids. So if in a synthetic scheme, you go around using a ketone or an aldehyde in some of these reactions, because maybe you can, right, you're going to get dinged. This is testing your knowledge on ketones, aldehydes, and carboxylic acids. Okay? So make sure that you have a ketone, aldehyde, or carboxylic acid along your synthetic schematic. Okay? Because otherwise, we're going to get ourselves into trouble. Does someone have their hand raised before I do the retrosynthesis?
Would we say that you can go from imines and enamines to aldehydes and ketones? It's reversible?
Yes, you could. Sure, sure. Yes. So these are reversible reactions. Just like this is a reversible reaction. Yes, yes. I think that's a fair assumption. Okay, so here I go. I have this alcohol, and I think that there are 3 ways that you can create this alcohol starting from a ketone or an aldehyde. So the question is, what 3 ways do you know, starting from a ketone or an aldehyde,
Grignard.
to get to Grignard for sure, okay, to get to this alcohol? The second question is, what methodologies do I know, starting with a ketone or an aldehyde, and maybe a one-step reaction? This is how I'm going to have to really get you guys, right? To get here, this is a Wittig. That's exactly right, okay? So the question is, what 2 methodologies will create this final product? So we're thinking backwards, right? And what 3 reactions would I need to create this product here? Okay? And then just as an outset, because people are having a really hard time with this, and I've been talking about it, I know Kim is talking about this in discussion, and I will do this and talk through this as well, and that is what to do with, say, something like this. If I added H3O+. You should be in 1 minute be able to figure out what you used to get to that. Okay? 1 minute or less. Okay, so we're going to talk through some problem like this. So let's work these in succession, just to make sure that we can do these types of problems. So when I think backwards, the carbon the OH is attached to, right? That was once my carbonyl carbon. So in essence, I can think of it as this was a new bond that formed, right? So this could have been my new bond, all right? So in this case, I would have used a methyl Grignard, okay? We call that path A. This could have been my new bond, right? We call that path B. That would have been a Grignard that's off of the alkene. And this could have been my new bond. Okay, we call that path C. Now, I know I can see an exam in the past, like because people have just been flipping through the bindings the last couple of days. I can remember an exam question just like this. Can you show what's necessary for A, B, and C? Okay? So, you should be able to do something like this. So, path A would be using this ketone and reacting it with a methyl Grignard followed by water and mild acid. Okay? Remember, the new bond means if this was my carbonyl side, I make that the carbonyl, and this here is what was added in a Grignard. There's only one carbon here, which is why it's a methyl Grignard. Okay? Path B here would be this ketone, adding this Grignard, followed by a mild workup. Yeah.
Can we use water with the Grignard?
Yeah, you can. Well, this is two. You guys are very confused by my 1, 2 still. 1, I add the Grignard, I get a negatively charged oxygen. 2, I add in some water, some mild acid, right, and it protonates that oxygen, clears out the magnesium bromide as salt, and I'm good to go. I got some product. Path C here then would be, that oxygen got lost down here, would be an ethyl Grignard, right? Is everyone good to go on these problems? This one's not too bad. Pause for reflection. Yeah.
Would we have to take into account like side phase, three phase catalyst?
Not in this problem, no. You weren't asked to. You could be, but no, this problem does not do that. Okay. So, problem 2 here is asking, in essence, what Wittig reactions you could use to get to this material. Okay? So, this here was my new bond, right? This was my new bond that I created in the course of the Wittig reaction. So when I ran that Wittig reaction, one of these ends could have been my carbonyl, and the other could have been what was attached to the triphenylphosphine originally, or vice versa, right? So again, one side had to be my carbonyl, and the other side had to have been part of my phosphonium ylide. Okay? So, in a potential 2 steps, so one path, path A we can call it, could have been saying, okay, I'm going to take this aldehyde, bless you, okay? So that's saying I'm going to take this aldehyde, 1, 2, 3, 4, that's an aldehyde because there's a hydrogen here, right? That was the carbonyl, it's an aldehyde. And an ylide, that's a 2-carbon ylide. So how do you write that? Write that as something like this. Okay? It's 2 carbons. If you are asked, oh my goodness, what was that? If you are asked to backtrack even further, you would have started from something like this, right? That would have been your starting material. And how do I do it? I run my initial reaction and then I add
Sodium.
begins with a B,
Boring.
something lithium, butyl lithium. That's exactly right.
Nope.
So to create my ylide, I would react these two, SN2, and then I would add butyl lithium, and it would create my ylid. Okay? Path B here is going to swap the placements. So I can say that I started from this aldehyde, and I had, oh my goodness God, I had to add a 4-carbon ylid. Okay, so in this case, I would have added this. I can count. All right. How are we doing?
Good.
These aren't so bad, right? Question?
Yeah.
Yeah.
What kind of situations can arise where one of those would be favored?
Ah, that's a great question. Okay, let's suppose I change this. I love when you do this. Let's suppose this was different. Okay, well we can. Let's suppose this was different and I had this. Okay, so I've changed what I'm trying to do. I still know where my new bond is. But in this case, I would have used, if this was what I had, I would have used this as my carbonyl side and this piece in my ylid. Because, and think about this, a good question. The reason is that I would guarantee an SN2 reaction in creating the ylid here, whereas if I flipped those, I'm going to have a harder time creating the ylid, because I would be trying to create an ylid at a secondary site with this neutral nucleophile, which has the propensity to run SN1, SN2, sort of in heavy competition. Okay? So I'm always going to choose the less substituted side of my alkene to be derived from the ylid. If I had differing substitutions, which my molecule on the board now does, there is one single path that's the preferred path, and that is keeping the more substituted side of the alkene as my carbonyl side, so that would have been derived from a ketone, my less substituted side where the ylid's going to form. Okay? Everyone understand that concept? If not, write it down, come on in, we can talk about it.
Wait, why is it thermodynamically favorable?
Because in this case, right, so what I'm saying is the heavy favored path is this path here, where I would have this ketone, and I would add my ylid, that's this guy, right? And that's because as I come back, right, so this is my starting material, I'd be guaranteed an SN2 because I have a primary site. So think about that. Okay. So this last problem on the board before we get to our reaction scheme that we can work with the remainder of the time is this one here. So this is something people have been having a hard time with. This is, honestly, I recognize that these all just look like crazy molecules with lots of oxygens and nitrogens. I'm with you. I get that. Okay? So the first thing I really need to do when I see any molecule is classify it. My choices are imines, enamines, acetals, heavy acetals, ketals, heavy ketals, right? Anything that's got all these oxygens and nitrogens. So I see only oxygen. So I'm not going to that imine and enamine section, right, of my brain. I'm coming back to 4 choices. I can have a heavy ketal, a heavy acetal, a ketal, or an acetal. 4 choices, okay? So I come and I hone in right on the carbon that's between the 2 oxygens. So I'm right here. That's the one I'm looking at, right there. Okay? And I pause for reflection. If I have an OH and an OR, I'm a hemi, right? If I have 2 OR groups, I'm a straight acetal or ketal. This is an example where I have an OH and an OR. OH and then an OR, carbon, right? So this is a hemi, so I know it's a hemi something. The other thing I need to do is classify what types of R groups, non-oxygen species, I have attached to that carbon. I have 2 remaining slots, right? One of them happens to be a carbon, and the other is a hydrogen, right? So this makes it a hemi acetal. Okay? So I know that this was derived from an aldehyde, right? It was derived from an aldehyde. recall a couple of things. One is that I'm always in acid, right? We can form these in the hemis we can form in base, but we said we're always going to use acid. So the first thing I need to do is not make this negative, right, but make it neutral. Okay? The second thing I need to do is what I know needs to happen. This has got to be my carbonyl carbon, right? This is my carbonyl carbon. So I'm going to make it my carbonyl carbon. And hence, now I have the framework of what I'm going to when I write out this reaction mechanism. This is the end product. And this is an intra-molecular reaction, right? Intra, meaning the nucleophile is in the same molecule as the electrophilic center. That's why a ring forms. Whenever you have a ring, an oxygen embedded in a ring, okay? Does everyone see this? Can everyone write the mechanism for this? We're not sure? Should we do that before we do the reaction schematic?
Yeah.
Okay. Okay. So I have this. And I know what I'm going to, so I'm going to write that up because I do want to track that as I come through. Okay? So before I even began, I'm thinking, what am I going to? And I've written it up, just like I did over there. So now I know I'm in H3O+. That's what has to happen, right, in order to get back to my aldehyde and nucleophile neutral alcohol. So I add H3O+. So I have H2O and H2SO4. I hope you recognize that your first step here has to be protonation, because I need to break something, break a bond, right? So I have an OH and I have an OR. Remember, if you're going back toward the ketone or aldehyde, you protonate the OR groups, not the OH. You protonate the OH, you're moving forward toward acetal formation, right? If you think in the forward direction, I can make an acetal from that hemiacetal. That would require protonation of the OH group, loss, and then pass in of another OR group. But I'm not, I'm going backwards. When I go backwards, I'm protonating all the OR groups until they're all off. That's my goal, okay? So I protonate my OR groups. So here I am, this is reversible. I get down to this guy here, which now is a good leaving group, right? Remember to always allow this group to be released from the carbon that's keeping the oxygens, okay? And not from the other carbon, because when I release from this side, I have a resonance stabilized carbocation. If I release from the other side, meaning over here, which is the no, I wouldn't have a resonance stabilized carbocation. Okay? Resonance stabilization is key. So I come out here, that can go off, it can go on. So now I have this guy out here. And there's my carbocation. I always want to show the resonance stabilization. So we could do that. And that looks like an awful lot like what I'm getting to, right? I mean, this is a dividing line here, because we're working mechanistically here. But they look identical, don't they? this proton and passing electrons back in. Okay? Everyone see that? All right, let's go schematic. Yeah, you have him. Yeah.
For this one, if we labeled it as a hemiacetal, why can't it go to become an acetal?
It can go to form an acetal. In this case, I would need to add alcohol and water and acid. That would go to acetal formation. But H3O plus is going to get me back to the aldehyde.
I thought you said it worked with even just H2O and like an acid.
Yeah, H3O plus is H2O and an acid.
Right, but then didn't you say that was the same thing as doing
So,
alcohol
okay,
and water?
so no.
Okay.
So I have two choices here. This gets me to backwards, right? I could have also taken this and gone forward. Say I want to add something like ethanol and an acid. This is still fully reversible. And what I get here is this guy here.
Okay.
So I get an acetal out of that. So if I move forward, that's adding another mole of alcohol, any alcohol, and acid. And if I go backwards, I'm adding H3O plus. Okay? Yeah.
Do we have to show the removal of water for like a neat start thing?
You need to show the removal of water. No. Yeah, like they do in lines. Yeah. No. Yeah.
With the last step, when the ether adds on, ether group, is that SN2?
When the water adds and the OR group adds
Yeah.
on, that's SN1.
Is SN1? Okay.
Yeah, all these reactions, I remind you, you're in alcohols really, right? You're in sort of an alcohol ether land. These all look like SN1 reactions. None of them have SN2 propensities, right? They're all more SN1-like than they are SN2-like. So that means carbocations form and then nucleophiles attack, right? So remember that. Carbocations form and then they attack. Where are the extra sheets here? There have got to be extras. There we go. 'Cause there's some back there too. Someone tell me the time. 12:45. Anyone need one still? Okay. Okay, great. I'll get them outside my office. Okay. I guess we don't need to really go over this. Does anyone have any questions about this? Yeah. This is not homework that's due on Friday, although that's a good idea, isn't it? You do have a homework coming out tonight, so, but no, I'm going to leave this as a weekly quiz. The answers will come out. You do have homework coming out tonight, though. It is due on Friday. But I want to make sure to test some things that haven't been tested. So, okay. So you guys are free to go. Homework will come out tonight.